Hey guys, and welcome back to another video. Today we'll be discussing 1.5 polynomial functions and behavior. Okay, so to begin with, let's talk about multiplicity. So multiplicity is simply the number of times a root is repeated in a polynomial. The number of times a root is repeated in a polynomial. Okay, good. So let's do some examples to illustrate this. So first of all, example 1. Let's find the multiplicity for each of the roots of g of x equals x minus 1 squared times 3x plus 5 to the 7th times x plus 5. Okay, so notice how each of these linear factors corresponds to one root of g of x. So for example, if we set this whole thing equal to 0, we get x minus 1 squared times 3x plus 5 to the 7th times x plus 5 all equals 0. So this is possible if any of these factors is equal to 0. So for example, we could have x minus 1 squared is equal to 0. We could have 3x plus 5 to the 7th is equal to 0. Or we could have x plus 5 is equal to 0. So here you get x is equal to 1, right? But since we have two factors of this, right, because technically this is the same thing as x minus 1 times x minus 1 is equal to 0, you technically get x equals 1 twice. And so that means that x equals 1 has a multiplicity of 2, since it's repeated twice. And the way we denote that shorthand is just a times 2 at the bottom. Okay, so this is basically saying that x equals 1, the root 1 is repeated twice. Okay, for this one, 3x plus 5 to the quantity to the 7th, that's the same thing as writing 3x plus 5 7 times. So here we just get x equals negative 5 over 3. But we have 7 of those factors, so the multiplicity is 7. And then here we only have one factor of x plus 5. So the multiplicity, which is of the 0, which is negative 5, is just 1. So just say times 1. Okay? Okay, good. Now let's go on to another example. Example 2. So now, let's say we're given the zeros of a polynomial with their multiplicities, and now we have to find the actual function. So let's say we have a polynomial. Let's say we have a polynomial with degree 7, and its zeros are negative 2 with multiplicity 2, 0 with multiplicity 4, and 1 with multiplicity 1. So our polynomial p of x is equal to, so to get negative 2, what factor do you need such that when you set it equal to 0, you'll get negative 2? Well, x plus 2, right? Because x plus 2 is equal to 0, you get x is equal to negative 2. And we have a multiplicity of 2, which means the power is 2, since we have two of these factors. Okay, and then next we have 0 with multiplicity 4. So for 0, you just need x, because x is already equal to 0. So just x to the power of 4. And then for 1, you should have x minus 1, and then to the power of 1. Okay, and then simplifying this, you get, we usually bring if we have any like x to some power term without any like constant added to it, we usually bring that out front. So we bring the x to the 4th out front, and then you have x plus 2 squared times x minus 1. And then, boom, that's our polynomial. Okay, cool. Now let's talk about even and odd multiplicities. So if you have an even multiplicity, which I'll just abbreviate as MULT, then that means the 0, which has the even multiplicity, is going to just barely touch the x-axis. It's going to touch it and come back. So for example, if we have some graph, and let's say that at x equals 2, it has a multiplicity of 4, right? So it's even. So the graph would just barely touch 2 and then go back up, right? So it just kind of bounces off the x-axis and goes back up. But on the other hand, for odd multiplicity, the function or the graph crosses the x-axis for odd multiplicity. So let's say you have some function that looks like this, or like some 0. Let's say you have a 0 at 2 again, but now the multiplicity of the 0 is 3, so it's an odd multiplicity. So now the function would probably cross the x-axis in some manner like that. Okay, good. And that's essentially all there is to know about even and odd multiplicities. Okay. So now let's talk about end behavior. So for end behavior, you have to consider two things. You have to consider the degree of the polynomial, and you have to consider the sign of the leading coefficient. So we'll say that n is our degree, a sub n is our leading coefficient, and then we have our end behavior right here. Okay, so make like a little table. So if n is even, so we have even degree, and our leading coefficient is positive, then you can just you can just think of a parabola, right? A parabola is x squared, so it has even degree, and it has a positive leading coefficient, right? So just think of a parabola, it looks something like that. So as x approaches plus or minus infinity, f of x is always approaching positive infinity. The only new thing about end behavior in this section is how we express it, how we denote it. We use limit notation, which is basically we write the limit as x goes to infinity of our function, in this case f of x, we'll say, is equal to whatever it is. So in this case is equal to infinity. But we have to have two limit expressions, right? Because you have to have one as x goes to positive infinity, and you have to have one as x goes to minus infinity. So we have to do another one, the limit as x goes to minus infinity of f of x is equal to also positive infinity. Okay, and then boom, that's the end behavior for a polynomial with even degree and a positive leading coefficient. So now what if we had an even degree and a negative leading coefficient? So for example, negative x squared. So I'm sure you already know that that's just the x squared just flipped over the x-axis. So it should look something like that, right? So now as x goes to positive or negative infinity, f of x always goes to negative infinity. So the end behavior would be the limit as x goes to infinity of f of x is equal to negative infinity, and the limit as x goes to negative infinity of f of x is equal to negative infinity. Okay, good. So now those are all the cases with even degree. Now let's consider all the cases with odd degree. So now let's say our degree is odd and you have a positive leading coefficient. So for this one, you could think of y equals, or f of x equals x cubed. So that looks something like this. This is x cubed. This is x squared. This is negative x. Okay, good. So now you can see that as x goes to infinity, f of x also goes to infinity. And as x goes to negative infinity, f of x also goes to negative infinity. So the limit, or the end behaviors, is the limit as x goes to infinity of f of x is equal to infinity. And the limit as x goes to negative infinity of f of x is equal to negative infinity. Okay, and then the final case is we have odd degree and negative leading coefficient. So then you could just think of negative x cubed, which looks something like this. And now notice that as x goes to positive infinity, f of x goes to negative infinity, and as x goes to negative infinity, f of x goes to positive infinity. So the end behavior for this one would be the limit as x goes to infinity of f of x equals negative infinity, and the limit as x goes to negative infinity of f of x equals positive infinity. Okay, cool. So the only new thing about end behavior in this lecture is just how we denote it, right? We have to use limit notation now that we're in AP Precalculus. Okay, good. So now let's do some examples with this. So I'll keep this chart up just to help us. So example 3. Let's say you had some function f of x equals x plus 2 times x minus 1 quantity squared. Okay, so you have to consider the degree, whether it's even or odd, and then the leading coefficient, whether it's positive or negative. So essentially we're just looking at the first term of the function because that tells us the degree and what the leading coefficient is. So we just have to FOIL out the first term, and notice that the first term is simply just x times x squared. So the first term is just x cubed and then plus a bunch of jargon. But if we just look at this term, we notice that it has odd degree. So our degree is odd, and our leading coefficient is just 1, so it's positive. So our leading coefficient is positive. So we're looking at this case right here, odd degree, positive leading coefficient. So that's our end behavior. So limit as x goes to infinity of f of x equals infinity, and the limit as x goes to negative infinity of f of x equals negative infinity. Okay, cool. And don't think that you have to memorize this chart. Just memorize the you don't have to memorize anything. Just like think about it in your head, because like for even degrees, you just think of like x squared, what it looks like for positive and negative leading coefficients. And then for odd degrees, just think of like the x cubed function, right? Like if you just think of how the end behaviors for that looks like, then you can automatically come up with a limit notation for that. So don't think that you have to memorize this table. Okay, anyway, let's do another example. So let's say you have some function g of x is equal to 2x to the 4th minus 8x squared. Okay, so here they already folded out for us, and they gave us our first term is 2x to the 4th. So here our degree is even, right? It's 4, so even degree. And then our leading coefficient is 2, so it's positive. So then we're looking at this case right here. So this is our end behavior. But let's say you didn't have this table. How would you do this? Well, even degree leading coefficient is positive. So just think of x squared, right? Because f of x equals x squared has an even degree and a positive leading coefficient. And then you can just think, okay, as x goes to positive infinity, f of x goes to positive infinity. And as x goes to negative infinity, f of x also goes to positive infinity. And so therefore, the end behavior must be as x goes to infinity of g of x is equal to infinity, and then its limit as x goes to negative infinity of g of x equals infinity. And this works because the end behavior for any even degree polynomial with positive leading coefficient is the same, regardless whether it's a quartic, a 6th degree polynomial, a quadratic. Any polynomial with even degree and positive leading coefficient always has the end behavior. Any polynomial with odd degree and negative leading coefficient always has this end behavior. So if you just have one example that you always can refer to in your mind that satisfies the degree and leading coefficient constraints, then you're good to go, because any polynomial that satisfies those restraints will have the same end behavior. And so that's why I recommend using x squared and negative x squared for the even degrees, and then x cubed and negative x cubed for the odd degrees. So those are the most easily visualizable functions, in my opinion. But anyway, that ends our lecture today. I hope you learned something, and thank you for watching. See you in the next video.